Okay, welcome to Chapter 3, Organic 1. Write structures for the following compounds. Okay, for this structure, we need to draw the hexane. And hexane has 6 carbons, so 1, 2, 3, 4, 5, 6. And then on the third carbon, we have ethyl. On the 4, we have methyl. Okay, the next one, no name. We have 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. And on the third, we have an ethyl. And we also have a methyl on the third. See the third? And then on the 5, we have isobutyl. And if you remember, isobutyl would have 4 carbons. And it would make a Y. Okay, the next one, C, heptane, 1, 2, 3, 4, 5, 6, 7. On the 2 carbon, we have a methyl. And then on the 4, we have a tert-butyl. Remember, tert-butyl is 4 carbons, and it makes like a cross. The last one, octane, so we have 8, 1, 2, 3, 4, 5, 6, 7, 8. On the third, we have trimethyl, so methyl, methyl, there's 3, and on the 4 we have methyl. So there's your trimethyl. And then on carbon number 5 you have an isopropyl, which is 3 carbons to make a Y. Okay, now for these we want to draw the IUPAC name, so let's draw them out. So here we have CH3, CH3, there's CH, CH2. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so you look for your longest chain, which would be this, and you want to get your substituent, which comes off the longest chain, the lowest number. So 1, 2, 3, 4. This would be 2-methyl butane. Okay, let's go to B. CH3 goes to carbon. This carbon has 2 CH3s on it, and then that's CH3. So there's that. Find your longest chain. So that would be your longest chain. 1, 2, 3. So you're looking at propane. And then your substituents are methyls. So you have 2-methyl, and then you have another 2-methyl. So you'd have to do 2, 2-dimethyl propane. Okay, the last one, here we have CH3, CH2, CH2, CH, CH2, CH3. So this is this one right here. And then this is connected to that CH. And then that CH is CH3, CH3. So count your carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. You find your longest chain. So that would be your longest chain. You want to give these, you want to go from right to left. 1, 2, 3, 4, 5, 6. So 6 is hexane. And then your substituents is a methyl, 2-methyl. And then you have a 3-ethyl. And you would want this in alphabetical order, so it would be 3-ethyl, -2-methyl, hexane. Okay, the next problem. In each pair of compounds, which compound has a higher boiling point? And explain. Okay, so the first one we do is octane. So draw out octane, which is 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. And the next one, you draw out pentane. 1, 2, 3, 4, 5. And then on the 2, you have 2, 2, 3 trimethyl. So you want to get how many carbons you have. 1, 2, 3, 4, 5, 6, 7, 8. That's C8. This one has 1, 2, 3, 4, 5, 6, 7, 8. So they have similar molecular weights. And they have similar function groups, okay? We call that functional groups because they're both alkanes. So you're looking at, this is the straight chain, and this is the branch. And this is the rule. If you increase your branching, you decrease your surface area, and that decreases your boiling point. Okay, so the first one would have a higher boiling point because it would have increased surface area. Increased surface area, you have increased boiling point. Surface area, increased boiling point. Okay, nonane, this is B, that's 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 2-methylheptane. 1, 2, 3, 4, 5, 6, 7. And there's your methyl. And so we have C9, and here we have 1, 2, 3, 4, 5, 6, 7, 8. C8. So in this case, C9, nonane, would have the higher boiling point because it has 9 carbons, so it'd have a higher molecular weight. Okay, C, we got to start with hexane. 1, 2, 3, 4, 5, 6. And then on the 2, you have 2, 2, trimethyl, 2, and there's your 5. And then the versus nonane, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 carbons. So how many we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is also 9. They're both alkanes. So the higher boiling point would be this straight chain, which would be like in nonane, straight chain, because you increase surface area, you increase boiling point. So nonane would be your higher boiling point. Okay, use Newman projection about the indicated bond to draw the most stable conformer of each compound. Well, if we're going to do the most stable conformer, then you know we have to draw a staggered. Okay, so we're going to be drawing this staggered conformation for both of these. So go ahead and figure out what the structure is. Draw the straight chain. So 1, 2, 3, 4, 5, and then on 3 you have a methyl. And it's about the C2, C3 bond. So here's the C2, and this is your C3. So this is your C2, which is red, and then your C3, which will make blue. Okay? So C2 has a methyl, a hydrogen, a hydrogen. So this has a hydrogen, and a methyl. Your C3 has an ethyl, a methyl, and a hydrogen. And you want to make sure that the ethyl is here 180 degrees from the methyl. And then you also have a CH3 and a hydrogen on the blue. And you do have a little Gauss interaction right here between the two methyls, but your bulkier group would be this ethyl group, and you want it to be 180 degrees from the red methyl. Okay, the next one, you're going to still do the same conformation. So let's go ahead and draw our Newman staggered conformer. Let's draw our structure. Hexane, 1, 2, 3, 4, 5, 6, and 3,3 dimethyl. And it's asking about the C3. There's your C3, make that red, and the C4 bond. So this is your 4 bond. So we'll make the circle blue. And so this has a hydrogen, and an ethyl group. So hydrogen, hydrogen, CH2, CH3. And you want that to be anti, so you want it to be 180 degrees. Now what do you have here? Off the red you have a methyl, and an ethyl. So you're going to put the ethyl at the top because you want it to be 180 degrees from the anti. You want it to be anti to this other ethyl group. and then you have a CH3 and a CH3. And that would be all on that bond right there. Okay, which of the following structures represent the same compound? Which ones are different compounds? So what I like to do is I like to name them, and then if they have the same name, then they are the same. If they have a different name, they are different. So this compound here, excuse me, you can put in your hydrogens there, and you can see that that's 2-butene, and it would be cis. So you can write cis, or you can do Z, which means cis. This one here is 1-butene, and it does not have cis or trans. This compound here would be trans 2-butene. This compound here would be cis 2-butene. So obviously this in this compound here, we'll call them number 1, and the red are the same. This one right here, 1-butene, would be the same as this 1-butene. And then this compound 1, 2, 3 would be 2-methylpropene, and it would be different. Okay, we're still dealing with cis and trans, different conformation. This would be cis 1-2-dimethyl cyclopentane. So these CH3s are on the same side because they're coming at you, so that's cis. This one's going back and it's on the same side, so this would be the cis, so those would be the same. This methyl and this methyl are opposite. One's on the up and this one's on the down, so that would be a trans. This would be trans because of the way it's drawn with the wedge and the dashes, so those would be the same. And if you look at this one, this is 1, 2, 3, so this is a 1,3 dimethyl cyclopentane, and we would call that cis, and that would be different because it would be a constitutional isomer because all of these other ones are 1, 2, and this is a 1, 3. The connectivity is different. Okay, so when you look at these compounds here, kind of find your longest chain, including your double bond, and give it a name. So in this case, it would be 1, 2, 3, 3-methyl, 3, 4, 5, 6, 3-hexene. 1, 2, 3, 4, 5, 6, and this would be, you gotta look at your heavier group here on the first alkene would be between the ethyl and the methyl. So this other carbon here would be between a hydrogen and an ethyl. So the ethyl and the ethyl are on the opposite side, so we call that trans, which is also E. Look at the next one, 1, 2, 3. So this is 3-methyl 3-hexene. And you got to decide whether it's cis or trans. So the first carbon you look at, and you're comparing an ethyl with a hydrogen, which are different. And then the other carbon, you compare a methyl with an ethyl. And you can see that the ethyl and the ethyl are on opposite sides. So that would be E. That would be trans. So these are the same. The first two are the same. The next one here, 1, 2, 3, 4, 5, 6. So we're looking, and you look at the first one here, you have the ethyl on this side, and then you look at the other carbon double bond, and the ethyl's on the same side. So this compound is cis. We look at here, we have a 1, 2, 3, 4, 5, 6, and then you have to look and see the first carbon, you're comparing an ethyl with a methyl. So the ethyl is the higher molecular weight, and the second carbon you're comparing an ethyl with a hydrogen, and you see that both ethyls are on the same side, so this is also cis. So these two compounds are the same. And then the last one you're looking at 1, 2, 3, 4, 5, 6. So you're looking at a 2, 3-methyl -2 hexene. And so this is different. The double carbon-carbon double bond is on a different carbon, so that would be a structural isomer. Okay, the last set here are Newman projections. So you want to just kind of draw the Newman projection. There's your CH3, and then this carbon here is your blue carbon. And if you look at this red carbon, you have another CH3. So this red carbon has 2 CH3s, and then the blue carbon has 2 CH3s. So that is a CH3 and a CH3. And so then we name this 1, 2, 3, 4. So it's 2, dash 3 dimethyl butane. Then you go to the next carbon, or the next structure, and the red carbon here is connected to a CH3 and another CH3. And then that red carbon is connected to this blue carbon right here, and it's connected to 2 CH3s. And if you name this, you'll see that it's 1, 2, 3, 4. It's the same structure, 2, 3. So these are the same. So then you go to the next one, and this red carbon has a CH3, a CH3, another CH3, and then it's connected to the blue, and the blue has 1 CH3. So what is the name of that? So 1, 2, 3, 4, so it's still butane, but do you see it's 2, 2 dimethyl butane. So this is different. This is like a structural isomer. Okay, going to the next one here, we have this carbon is a CH3, and it's connected to the blue carbon. And so this blue carbon is a CH connected to a CH3, connected to a CH, CH3, CH3. And then we count this 1, 2, 3, 4, 2, 3 dimethylbutene. So this is the same. So these are the same. So far, these are the same. Let's look at the last one here. We have a CH3, and it's connected to the blue carbon. And that blue carbon is connected to a CH3, connected to another CH3, and is connected to a CH2, CH3. And if you do the name on this, maybe 2, 2 dash dimethyl butane. And that is the same as this compound here. So these two are the same. Okay, this is assignment 3-2. And this is the last assignment for chapter 3. Write structures for the following compounds. Cyclopentane. So cyclopentane, heptane. Cycloheptane is 7. So let's see, 1, 2, 3, 4, 5, 6, 7. And we have 1 ethyl. There's the ethyl. And 2, 3 methyl. So there's the 3 methyl. And that is your structure for A. Okay, for B, you have hexane, cyclohexane. See the cyclo? So let's make cyclohexane, and then we have isobutyl. So isobutyl. So how many carbons would that be? That would be 4. 1, 2, 3, 4, and it makes a Y. C, cyclopropyl, cyclopentane. So go ahead and draw the main cyclopentane, And then cyclopropyl would be the substituent. And then D, let's go to cyclohexane. There's cyclohexane, and then 3,3-dimethyl. So 3-dimethyl butyl. So let's do butyl here. 1, 2, 3, 3, 3, 2, 3, 1, 2, 3, 4, and then 1, 2, 1, 2, 3. It looks something like that. This is a difficult one. And then that's on carbon number 4. So that's carbon number 4. And then on carbon number 1, so 3, 2, 1, you'd have 1,1-diethyl. So it looks something like that. Okay, name the following compounds. Remember that 2 up bonds are cis and 2 down bonds are cis. 1 up and 1 down are trans. So here we have cyclohexane, and you see that the methyls are both up. So that would mean that the hydrogens are up. So this would mean these are both down. So that makes them cis. And then you count 1, 2, 3. So this would be cis. So this would be cis 1, 3 dimethyl cyclohexane. Okay, going on to the next, you look, you have, this would be cyclohexane, and then you see that this hydrogen's up and this hydrogen's up. So you count your carbons, 1, 2, 3, 4. So this one would be 1, 4 dimethyl cyclohexane, and since both the methyls on the same side of the ring, it would be cis. Now the next compound, you have methyl up because it's axial up, and this is methyl down, and so that's on carbon number 1 and carbon number 2. So this would be trans dash 1, 2 dimethyl cyclohexane. Okay, this compound is a bicyclo. So you see that this is a bicyclo compound because it's joined right here. Bicyclo. And what you do with bicyclos is you write bicyclo, and then you have these brackets. And we're going to fill in this number, dot, number, dot, number, in these brackets. And these numbers are the carbons in the largest ring first. So that's 1, 2, 3. So that would be a 3. And then the next ring, it's 1. And then the last ring, it's 0. So it's 3, 1, 0. And then you count the total number of carbons. You have 1, 2, 3, 4, 5, 6. So that would be hexane. So it would be bicyclo 310 hexane. Okay, let's go to the next one. You see that that's a bicyclo. We're going to do our brackets with our numbers, dot, number, and then the brackets. So let's look at our largest ring, which would be 1, 2, 3. So put a 3 there. The next one would be 1, 2, 3. Put a 3 there. And then the one in the middle is a 1. And then you add up all of the numbers of carbons. So 3 plus 3 plus 1 is 7, plus these bridgeheads where they're connected and they're shared. So 3, 6, 7, 8, 9. 9 would be no name. You write no name. Okay, the next one we have bicyclo. And we're going to do our brackets with our dot and So when we look at this, we see that the first one has 2 carbons, so just put a 2. The next one has 2 carbons, and then the one in the middle has 2 carbons. And so 2, 4, 5, 6, plus the bridgeheads, 8, that's octane. We just put octane at the end. Okay, the last one we have is bicyclo. You do your brackets. And the first large ring would be the first one here. So 1, 2, 3. So we put a 3 there. The next one is 1. So we put a 1 there. And the middle ring has 1. So we put a 1 there. And then we count them all up. 3, 4, 5, plus our bridgeheads. 6, 7. So we write heptane. Okay, so the next the next problem is 3.2. Draw the most stable conformation. Okay, so we're doing chair conformations because you see each one of these are cyclohexanes. So we're going to draw our cyclohexane chair, and then what you want to do is draw in your hydrogens axial. That's down, up, down, up, down, up. Okay, so axial, down, up, down, up. And then what you're going to put here, cis 1 tert-butyl 3 ethyl. So they have to be on the same side. You always want your largest group, so what are you looking at here? You're looking at a tert-butyl and you're looking at an ethyl. Okay, so you want your largest group to definitely be, because you're looking most stable, equatorial. So we'll just make these both up because they've got to be on the same side, cis. So we're going to make them up. I'm going to go ahead and do equatorial up with my tert-butyl here. And that's going to now be carbon number 1. And then carbon number 3, we can go clockwise or counterclockwise, would be this one here. If that's going down, then this is going to put this ethyl as equatorial up. And that's the answer to A. Okay, let's go with B. You draw your cyclohexane. Go ahead and draw your axial hydrogens up, down, up, down, up. Okay, because we can always erase them. And then we want to do trans 1 tert-butyl. So once again, we're looking at tert-butyl and we're looking at a methyl. So those are our substituents. Okay, so we're just going to go ahead and put this tert-butyl up because we want an equatorial. And because it's trans, on the 2 carbon, it has to be opposite. And since that's up, this methyl goes here, and that would be your most stable. Because you went ahead and got your largest group, which is your tert-butyl, and you have it in the equatorial position. So that's going to be your most stable. Okay, for C, draw your cyclohexane ring, your chair, and then go ahead and draw your hydrogens down, up, down, up, down, up. So those are all your axial hydrogens up and down. And then you're going to see that trans 1 tert-butyl, so we got tert-butyl again, and this is on 3 you want propyl, and you want 1,1 dimethyl. So that would be my guess here. It's hard to say which one's going to be bulkier, but I would just go with ahead and keep with putting my tert-butyl in the equatorial. So that's a bulky group. It's an equatorial, and that's on carbon number 1. And so then on carbon number 3, which would be this one, we're going to put this other group, and we got to make sure it's the opposite. So if this is down, then the hydrogen has to be up, and then you'd have to, instead of have a hydrogen there, you would have to have this other bulky group. And you can just put that there. And that would be your compound. Trying to make it look better. So this one's equatorial up, and that would be axial down. Okay, question number 4. Which of the following structures represent the same compound? Well, just name them. So this is 1-4, 1, 2, 3, 4, dimethyl cyclohexane. And since they're both wedges coming at you, you would call that cis. They're on the same side. This compound is also 1,4-dimethyl cyclohexane, but it would be trans because they're one methyl's going at you and one's going down. Okay, so for this compound here, this would be 1-4-dimethyl cyclohexane. It's the chair conformation. But as you can see, the hydrogens are both going up. So that means that the dimethyl are on the same side, and that would be cis. So this compound and this compound are the same. And then your next one here would be a 1,3-dimethyl cyclohexane. And then you look to see that both hydrogens are going up, so that means these methyls are on the same side. They're both below the ring, and they would be cis. And the last one here, so this would be a different compound. The last one here, you can go 1, 2, 3, 4. So this one's going to be 1,4-dimethyl cyclohexane. And you can see that this is above and this one's below, so they're trans. So the trans compounds here would be the same compound. Okay, problem number 5. Draw 2 chair conformations of cis 1,3 dimethyl cyclohexane and label the position as axial or equatorial. Label the high energy conformation and the lower one. Okay, so we're going to draw both chair conformations, and we're going to have to flip them. And so this carbon here will then be up. And I can do better. So, okay, so this is that carbon there. Go ahead and draw in your hydrogens, your axial hydrogens. So up, down, up, down, up. This one will go up, down, up, down, up, down. Now we can figure out what we need. Cis 1,3-dimethyl. So they have to be on the same side, and we'll make them equatorial. So we'll just go here, and that's 1. There's 2. This is 3, and that's down. So this goes up, CH3. And then we come over here. Now this carbon here is this carbon here. And so this would be axial, and so now this would be CH3. So this one's CH3, see that? And that's 1, and then 3 would be CH3. And then your hydrogens would be equatorial down. These are now axial. So when you flip them, they go from equatorial, the substituents, to axial. But you see how they're above the ring, so they're up, and they're on the same side? They still stay up, and they're on the same side. And so, but which one is lower energy? The equatorial. So this would be lower energy. When you put those methyl groups, they have this Gaussian interaction right here in the axial position, and that would be higher energy. Okay, so this exercise you're supposed to do the 2 chair conformations of each compound, label axial or equatorial, and determine the more stable. So this will be good practice for you. This is your carbon here, and this is your carbon here. Just get in the habit of go ahead and draw in all your axial hydrogens, especially since you're just starting. It's good practice to do, and then you can always erase them. Okay, so I like to go ahead and make my more stable one. So we're going to do an ethyl, and then we're going to do an isopropyl. We're going to put it on the 1 and the 2. So I just go ahead and put in my isopropyl in the equatorial. And since this is equatorial up, that's going to be on carbon number 2. So carbon number 1 would be this one, and it would also have to be up because cis is on the same side. So this is going to be CH2, CH3, and then you could draw in your equatorial. So this now is axial up for the ethyl. And so when you flip it here, this is your carbon number 2, and now it's equatorial. Nope. Yeah, I can draw this back in there. Okay, so what you have here then is it'd be, go ahead and draw this isopropyl here. That would be axial up, because what's up has to stay up, but equatorial goes axial, and then this would be equatorial down. And then you would go back to this carbon here, the carbon number 1, and that would be, that's axial over here, so it would be equatorial over here, and it would be up. So it's equatorial up, and they're both on the same side, so they're cis. And the isopropyl in the equatorial position would be your lower energy. Okay, so for B, go ahead and draw your flipped chair. And then we're going to draw in our hydrogens. I'm not going to draw all of them, I'm just going to draw a few of them. So that's axial up. So we want 1, 2. So if you do the isopropyl and equatorial down, then this would have to be trans, so you're going to have to go up, and it's on carbon number 1, so this is the ethyl, and it's equatorial up. Now, with both of your substituents in the equatorial position, this is going to be your lower energy. And we haven't even drawn this one yet, but let's just make this your, so now this is going to go, this is axial, because what's equatorial becomes axial, and this is down, and it stays down. And then carbon number 2 is equatorial up, but it would be equatorial, it would be axial now, up. And then your hydrogen then would be a hydrogen there and a hydrogen there. And this would be your lower energy. Okay, let's do C. And we're doing 1 and 3 for your substituents. So I'm just going to draw in my hydrogens on the 1 and the 3. And this is your carbon here from the flip. And we're going to see, so 1, we're going to go with an ethyl. So that's going to be equatorial down. And then on carbon number 3, it needs to be on the same side. And that's just going to be equatorial down as well. And because both of those are in equatorial, that's going to be your lower energy. This carbon here is now this carbon, and you can go ahead and just write CH2, CH3 over that hydrogen, because what stays down must stay down, and now equatorial is axial down. And then if you go to carbon number 3 and make that a CH3, that's axial down and hydrogen equatorial. Okay, so that's C. Okay, just a few more. D is trans, so let's go ahead and draw our two chairs with the flips. And we're dealing with 1 and 3, so I'm just going to put in the axial for the 1 and 3. This is now our carbon here. If it points down, I make it down. And we're dealing with an ethyl and a methyl. So let's go ahead and put the ethyl in the equatorial position, and that's going to be carbon number 1. So then carbon number 3, it has to be on opposite sides. So carbon number 3 has to be axial up. This is equatorial down. And that's going to be your lowest conformation energy, because your larger group is the ethyl group and you want that in the equatorial. Go ahead and draw the flipped. That's going to be axial down, because equatorial goes to axial. And then on carbon number 3, this goes to equatorial up, because axial up over here, so it'd be equatorial up over here. Okay, 2 more. Go ahead and draw your ring and your flip. And we have a 1 and 4. So I'm going to just draw my hydrogens for 1 and 4. Down, up, down, up. And then I'm going to fill in a 1 ethyl. The ethyl is larger than the methyl, so I'm just going to go ahead and put that equatorial, and that happens to be down. So then I'm going to go over to carbon number 4 here, and it has to be down as well because it's cis. So I'll just go ahead and change that hydrogen to a CH3, and then that would be axial down. So they're both down, which is cis. And then when it flips, it's going to be equatorial down, and it will be, oh, not equatorial down. Here, erase that one. Okay, so if it's down, it's got to stay down. So this would be equatorial down. And this carbon here would be axial down. And then the last one here, go ahead and draw your lip. And you have carbon number 4 and carbon number 1. So I'm just going to draw my hydrogens going up, down, up, down. We have an ethyl and a methyl. So go ahead and draw the ethyl on carbon number 1. And this is equatorial down. We have trans. So over here, if that's down, this needs to be up, CH3. So this is equatorial up. And that makes them trans because one's up and one's down. This is going to definitely be your lowest energy, because both substituents are equatorial. And then here, what's equatorial, it's down, becomes axial down. And then you go to carbon number 4, and equatorial becomes axial. So it's equatorial up, and now it's axial up. Okay, last question. The most stable form of the common sugar, glucose, contains a 6-membered ring. in the chair conformation with all the substituents. Draw this conformation. So, to draw this conformation, you would just draw your chair conformation, and then here you would put this oxygen right here, and then it says that they're all equatorial. So go ahead and draw your hydrogens in. Up, down, and then let's call this one here, and this would be equatorial CH2OH, and that would be equatorial up, and then this OH here would be equatorial down. This OH would be equatorial up. This one would be equatorial down. And then this would be equatorial up. And so then if you were to draw this in a flat ring, you put your oxygen here, and then everything that's up would get a wedge at you. So that's this one. And everything that's down would go back. So this would go at you with a wedge, and this carbon would go down, go back, and then this carbon here is above the ring, so it's up, so we would get a wedge. And that is the structure of glucose.